actually figure it out. It's a little, I'm missing something small that I'm just missing. Alright, so anyways, back to this. The E cell of this, the voltage would be cathode minus anode. So, the cathode is, who's got that? Read me the number. 0.8. 0.8?
Yep.
That's Ag plus an electron yields Ag solid, so that's 0.8. Alright, so 0.8 minus, now the anode would be the, so that's good, because that's Ag plus, right? That's what's going on in here. You don't have Ag plus 2, or it's Ag plus gaining an electron, so that, when it gets reduced, that's what happens. Now, if you write the balanced equation, yes, you need 2 of those for every one of these. But it's still only 1 Ag plus and 1 electron. That's the ratio. These standard reduction potentials are constant numbers, right? So we don't have to worry about that. But anyways, that's 0.8. 0.34. I just want to find it here. 0.34, there it is. So, and again, even though the copper is losing electrons, creating copper ions, the way it's written, the standard reduction potential, right? The way it's written in this chart, it's always the ion gaining electrons. That's why it's cathode minus anode. That kind of, I don't know if I need to really explain this fully, but the reason it's cathode minus anode is because the way it's written is backwards, right? So that this equation here corrects that mistake. So that's why this is going to be positive. So 0.34. 0.8 minus 0.34, so what is that? 0.46 volts. Okay, so that's the voltage here created from this cell. All right, now, how do we solve delta G? What's the equation? Delta G equals?
Negative
Just give me the variables.
NFE.
NFE cell. All right, so equals. Now, how many moles of electrons are being transferred here? 2. Because the balanced, here's what's happening here. Cu yields 2 electrons, Cu plus 2. Over here, it's 2 Ag plus 2 electrons yields 2 Ag 0. So you have to double the coefficient here because of the balanced chemical equation. So overall, it would be Cu plus Ag plus yields Cu plus 2 plus Ag 0, 2 of those, 2 of those. So that's like the overall balanced redox reaction. We don't really care too much about that. You just have to understand if it's a plus 2 and a plus 1, we need 2 of these, right? Because think of it this way. Copper is losing 2. So you have 2 electrons going through this wire. So you have 2 electrons coming in here. So what that means is you have 2 Ag pluses that are reducing. 1 Ag plus gets 1 electron, 1 Ag plus gets the other. So it's still 0.8, right? It's still Ag plus gaining 1 electron. It's just, it's happening at 2 at a time. Okay, so this is 2. That's the whole moral of the story. All right, there's 2 electrons flowing from one half cell to the other. That's why that N is 2. Faraday is 96,500. So that's coulombs per mole. That's mole. This is 0.46 volts. And what do we get? I made this up, so I don't have a number. Like I just did this said, all right, we'll do this. So I don't know any answers here. So what's all that added to? And now remember, this is in joules per mole.
88,766.
What is it?
87,66.2.
Joules per mole. If we convert that to kilojoules, it's 88.77 kilojoules per mole. So there's my delta G. Oh, negative, right? Negative because that's negative and that's positive. Positive E cell means it's spontaneous, thermodynamically favorable. Negative delta G means the same thing. Now, since this is thermodynamically favorable, what should K be? Greater than 1, 1, or less than 1? Or 0?
Wait.
Let me rephrase that. Should K be greater than 1, 1, or 0? Greater than 1. If it was 0, what does that mean again? Not K, sorry. piece. If K is 1, what does that mean? It can't be 0.
It favors products.
If K is equal to 1. Remember, K is products over reactants. So if it's equal to 1, these are equal. What's that mean about the cell? It's at equilibrium. If K is equal to 1, what is delta G?
If it's greater than 1,
It's at equilibrium. If K is 1, it's at equilibrium. What's delta G's value at equilibrium? 0. If it's below 1, negative number, we're going to the product side. We're favoring. Thermodynamically favorable. Spontaneous. If it's greater, if it's positive, it's not thermodynamically favorable. It wouldn't work. It'd be going the wrong way. This is why I wanted to do this with you, because it's reviewing everything we went over last week. Plus, we're kind of doing something new with the K. We didn't really practice that. So, if you are given the values, I expect everyone to be able to calculate these two. Because this is on your reaction sheet, equation sheet, whatever you want to call it. All you need to remember, really, 2 things. Cathode minus anode, that's one thing you need to remember, and how to balance these equations so you get N. F is given to you, E cell is from the first thing you got to remember, cathode minus anode. Again, this is really easy, because they have to give you the numbers. No one's asking you to solve for that. So they're going to give you the numbers, just cathode minus anode. Once you have that, you plug it in, you just need to remember how many moles are transferred, how do you figure that out, the balanced equation. They may not give it to you though. Alright, this isn't Regents, this is AP obviously, you know that, I don't need to say that. They might just give you this and you have to figure out how many moles, right? You just have to balance it yourself. So, now you have this, how do we solve for K? What's that equation? What's the connection there? How do we solve for K?
R2 on K.
Right, delta G equals negative RT natural log of K. Alright, so delta G, negative 88.77 equals, actually, you know what, we can rearrange it here. R is 0.008314. Temperature is 298. That's all equal to the natural log of K. And if you want to get, more crazy here, you can just do this. Negative 88.7 divided by 0.008314 times 298. So all of that, e raised to the negative, all of that equals K. So there's nothing new, really, except we didn't really practice a whole lot with converting from delta G to K. But we've done this before. We talked about this stuff last week. I know it was only one day, but that's why I wanted to do this. I wanted to do another problem with you here. I'm going to give you a couple homework problems, practicing the same thing. So go ahead, solve for K. Just remember, if this G is in kilojoules, you got to make this 0.008314. It might be easier just to leave delta G in joules, because then you can leave R. It's really a preference, so it doesn't matter. I'm just used to kilojoules for some reason. So solve for K, I would expect it to be above 1.
The number's below 1.
Yeah.
We got 2.8 times 10 to the negative 16.
It's going to be a big number.
They got negative. Nicole, did you get negative? Did you make R negative?
You're killing me, Smalls.
Is it 3.6?
Wait. 88.77 is supposed to be negative with another negative attached to it. So
No.
that should be a positive.
Yeah.
Because our delta G was
Remember-
Oh, I forgot my negative down here.
Yeah.
Sorry. You're right. Sorry. You're right. So that's a positive number.
Yeah.
So this? Is that what you want? What you want? It's in there. Or to the 32. What are your 32?
Three point six.
Oh, I didn't
Just
just
fine.
Yeah.
Alright,
Alright,
I got a number.
6 times 10 to the 15.
Yes. 3.6. So that's on me. Sorry. I'm killing myself. So, this is, it's E. So when you hit second natural log, it's supposed to be E to the negative of that value, which means it's positive. So that's negative, that's negative. So it's really E to, this is a positive value. So it's 3.6 times 10 to the 15th. That's my fault. Sorry, guys.
That's the right answer, so
Yeah. Yeah.
You're welcome. I saw
Okay.
it.
All right. So one thing I want to stress before I move on here is these numbers in the reduction potential chart are not affected by coefficients. It's kind of like the delta H. The Q will change, so that the problem that is you're going to do for tomorrow, the one that I took a picture of, the delta H will stay constant because it's joules per mole. So when you use it, so stay with me. Let me first go back and then I'll come back to this. If you use 1 molar HCl and NaOH or 2 molar NaOH and HCl, I don't know why I did that. So both of these will produce the same delta H because the delta T here will be higher. So when you do Q equals MC delta T, you're going to get a larger Q because there's more moles reacting. So there's more heat. That should make sense. But the actual heat of neutralization is in kilojoules per mole. So you're going to have a greater number of moles here. So that number on the bottom goes up proportionally to this number on top. So even though your Q's will get larger, that's why I gave that problem. I'm going to talk about this again tomorrow when I go over it. The Q will change, but the moles will also change, so your delta H is going to be the same. If you look up the heat of neutralization for HCl and NaOH, it's a standard number, negative 56.2 or something. So it doesn't matter if you use 10 moles or 1 mole, because it changes proportionally. These reduction potentials and this problem, it's the exact same thing. So whether I have 1 mole, so that silver number, what the heck was it again? 0.8. Whether I have 1 mole of Ag plus or 2 moles, the number of electrons will proportionally change with it. So that 0.8 doesn't change. So hopefully that makes sense to you. If it doesn't, not a big deal. Just remember you never change those numbers. If you can remember that, then you're good. Okay? Because that's where the AP test will get some kids. They will give you the reduction potential for this cell, the one we just did. And some kids will say, oh, there's a 2 in front of the AG. I have to multiply that 0.8 by 2, and then the whole problem's shot. Don't do that. It's intensive property, meaning it doesn't matter how much you have because all the other changes change proportionally. So that number stays the same. So that is kind of like a longer problem that you could see, short answer, where they give you the voltaic cell and ask a whole bunch of questions about it. All right? Okay. I'm going to draw a picture. I want you to draw it. We'll introduce this and then pick up with it.
The whiteboard or notes?
Oh, no, sorry. No, so yeah, put the whiteboards back, please. So I'll give you 2 or 3, just like we did for homework. I have one in the notes that I'll just take a picture of, and then there's 1 or 2 in the book. So I'll get that to you as soon as possible, because I know you have, well, actually I have time, because 4 and 5 are flipped, so I'll get it to you by 4th. Because I know Skylar has study hall, and who else, Liz, Chi-Chi, or Taylor maybe,
Yeah.
or a bunch of you. I don't know. All right. Okay, so I'm going to draw a picture here. and we'll see if you can make sense of it. All right.
We'll use the quiz on that.
You're doing musical?
Correcting it today. What, like 4 points back or?
No.
Great what we did. You want it back.
4 pages of notes left in my notebook. That's it. How's that feel?
Actually refreshing.
Scary? Relief?
Scary, relieved, both maybe? All right, draw this.
I want to know. I asked you a question.
All right.
Look what,
What?
I would like to know.
You asked me a question?
Keep
Yeah.
ignoring
Just call me
me.
dude. What's up, dude?
3 times.
What?
Did you enjoy the musical?
Oh, I did. Yeah. I enjoyed it thoroughly. When Ben came on stage, I almost cried.
Did you
That
see
was
the
my
nitrous
favorite
oxide? Did you laugh at
Yeah,
that?
yeah, I did laugh at that, and then I thought to myself, I wonder how many people know the formula for that. And how it's not nitrogen dioxide. But anyways, yeah, that was.
I told Taylor, I was like, McCoy's probably in the back laughing his butt off right
I
now.
was because of multiple reasons. One, because Ben, and two, because of nitrous oxide. Anyways.
Did you see me come out as a man?
What?
Did you see me come out as a dude? You played like 3 different
I saw you in the beginning as like, were you a hobo or something? Or one of the dancers?
I was a
or what?
girl,
You were
yeah.
a girl, I don't remember. It was Friday, that was a while ago.
You didn't see me come out as a man?
No, I guess not.
Oh,
Maybe.
that was the
That
funniest
was a
part.
fun change.
That was
Yeah.
the funniest
No, it was
part.
good. And then you were Ariel at the end, so that was good.
Your daughter would have loved it. Should've gone.
Probably, but she was too busy probably actually not sleeping. All right. So, here's, draw this picture. Yeah, no, I enjoyed it. You guys did a good job. It's a lot of work. So, it's good. It's good. Are you glad it's over?
Yeah.
Kinda.
I didn't know as many of you were in it as you.
Yeah, I had to sit under that desk for the first 4 songs.
That's crazy. Wait, were you two supposed to get stuck on there?
No.
Okay. That was funny. That was really funny. Because Tristan's
I
just
got
standing
a
there like
earful
this,
after.
kind of looking, and
She
then
told
Nicole.
us to do that, but she forgot to tell us to go take our bows first.
Okay.
And then she came back and like yelled at us.
I wasn't sure if you were supposed to do it or not, but I laughed at that.
It was supposed to be like a surprise at the end.
Yeah. All right. Fair enough.
Tristan had no idea.
No, I enjoyed it. I enjoyed it. It was good. All right. Here we go. Now, in this cell,
Spell's gonna ring.
well, 3 minutes. Here we go.
Your own
This
spell.
is nickel. This is also nickel. This is nickel plus 2. This is nickel plus 2. This thing's called a concentration cell. Concentration cell. Write that somewhere here. So a concentration cell is how your nerves work. There's a concentration of ions, let's say potassium or sodium, in your body flowing in and out of cells, including nerve cells. The difference in concentration creates electric impulses, electricity essentially. And this kind of explains how it works. There's a natural flow, a natural progression of these ions and the electricity. So the way it works, let's just say this side is our oxidation and this side is our reduction. So that would make this one our cathode, anox, red cat, this would be our anode. So you can use nickel metal in both solutions, and both solutions can have nickel 2 nitrate. So literally both are the exact same thing. That's how this is a little different than what we just talked about. So usually it's 2 different metals. The more reactive metal is always oxidized, the less reactive is always reduced. But if it's the same metal, how does that work? It's different than concentration. This solution would be 0.1 molar and Ni plus 2. And now this one would be, let's say, 1.0 molar Ni plus 2. I technically should have 0.1 here for that. All right. So I know I'm running out of time, so I'll just explain the concept here and we'll pick up with it, I guess not tomorrow, Wednesday. So the way this works is we need the concentration, so just give me 1 more minute. The concentration of this cell and this cell must eventually be equal. Now, what number, okay, one of 2 things, either this number needs to get larger or this number needs to get smaller, or both.
Both need to move.
Okay, good. And when it does that, it's at equilibrium. This is spontaneous the way I drew it. We'll talk Wednesday about why. Who's here tomorrow? 1, 2, 3.
And then Trevor if he shows up.
Alright. So Ben, you know what? We'll just take care of everything tomorrow in
We're like
class.
C645.
And we're gonna do just practice AP problems.
Wait, so I
And actually, you know what we can do, Nicole and Cal? I'll send the homework out. You can do it for tomorrow, or I'll let you do it in class if you want. What's up to you? But I'll give you time to do that if you need to. All right, everybody have a good day.